See, that's why you leave your phones at the front desk if you take a, yeah, no. Tempting. So let's knock this out, and we're going to use the factor label method. So our first term is going to be our milliliters that we want to convert to cups. And there's more than one way to skin this cat, so I'm going to show you how I do it. So to kind of show you the flow, we're going to start with mils and end with cups. So milliliters are metric and cups are English, right? So we're going to have to do something there. Now, you don't have to memorize the relationship between liters and gallons. I would give that to you, or somebody would give that to you. But assuming we look that up, can we kind of fill in the blanks, like milliliters to liters and gallons to cups? So this is one you'd look up. Is there any uncertainty in that 3.785? Yeah. The only thing between metric and English that's exact. What's one thing between metric and English that's exact? Inches to centimeters, exactly. That's the only one. So there is uncertainty in that relationship. How about this equivalency statement? Is there any uncertainty in that one? Nope. That's exact. How about, and I'd have to think this through, how about this whole 1 gallon is equal to 16 cups? Any uncertainty there? No, because we set it up that way. Smart English people like us. So it looks like from each equivalency statement, remember, we can make a conversion factor, like a little ratio, make sure units kind of ultimately cancel down the road. So we can have 3 little terms here, 3 little ratios to get us from mils to liters, to get us from liters to gallons, to get us from gallons to cups. So our first term's going to be, dun, 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 the thing we want to convert. I always do that. And I put it over 1. If I didn't put it over 1. Okay. I always put the thing I want to convert over 1. And the reason is I want to emphasize that those units are on the top, the numerator. So do you see why on my way to cups, if my strategy is to go through liters, do you see why if I use 1 liter over 1,000 milliliters, milliliters cancel off liters? I should have asked you what goes next, but I bet you would have told me in this scheme of things, if I wanted to go from liters to gallons, I would use this equivalency statement, and I would insert it like that. Okay, does that make sense? Now I'll ask you, the last but not least, if we want to go ahead and go from gallons to cups, what number goes down here in the bottom? 1 gallon. Very good. And what goes on top? 16 cups. Exactly. That's it. And you do one last like crossover things. So milliliters cancel, liters cancel, and gallons cancel. Okay. So now this is where I bet you guys are all okay with this, that you kind of think of one long divisor kind of connecting those 4 terms. And so number-wise, we got the right units. Okay, liters, gallons, we got the right units. Number-wise, we can kind of think of it as in the numerator 275 times 1, I'm not going to write that down, times 16, divided by, in the bottom, 1,000 times 3.75 times 1. Oh, thank you. 2.785. Very good. So we kind of think of this as the things we're going to multiply and divide together. So our calculator is going to display something. One last look at how we're going to round this. Are we going to round according to decimals or significant figures? Sig figs, exactly. Hands up. How many sig figs? It's like a draw. Who thinks, do you think this, I know, I saw some 2s up there. But why isn't it 2?
Because 2 to the 16 is exact.
Right. Tricky, exact. So if it's not 2, how many is it? 3, yeah. Very good. 3 there. This is exact. Okay. And there's uncertainty here, but how many sig figs there? Yeah. Okay, so 3 wins out. Very good. Dun, dun, dun. Is that what Siri said? Oh my gosh. I didn't know she'd do that. 1.16 cups. Any questions about that? Good chance you could Google it and come up with an equality between milliliters and cups, you know, and drop that puppy in there. Okay, let's do another one with regard to length. Aside from the story problems are notorious for giving you a lot of blah, blah, blah. But aside from the blah, 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 basically we're going to go from 120 miles to kilometers. This number right here for 120 miles, how many sig figs is that? 3. Very good. Because that decimal is there explicitly put. So I have the direct method and the indirect method. Because you probably didn't commit this one to memory. Maybe you did. I didn't. Yeah. Why doesn't that surprise me? I'm not that geeky. So is this an exact relationship? No. It's an approximation. One cool thing about the English system is the 1 mile is exactly equal to 5,820. What? Is this, right, feet, yeah. 5,820 feet. Okay, that's exact. Yeah, that's exact. 5,280 feet? Thank you. Okay, so let's knock this out. You don't have to commit this relationship to memory between the English miles and the metric kilometers. So I start with the thing I want to convert. Now, what is going to go down here in the bottom here? 1 mile. Very good. What's going to go on the top? Kilometers. Yeah, 1.609 kilometers. So would we be done with regard to, do our units say we're done when we multiply these two together? Miles cancel and we're left with kilometers. So let the units do the heavy lifting. How are we going to round this? I see 3, yeah. Can't fool you guys. So 193 kilometers. So I'm going to show you the indirect one. And the indirect one, since this is English to metric, what's the thing with regard to length you guys told me? The English to metric, the exact relationship. 1 inch is exactly equal to 2.54 centimeters, yeah. So we're gonna do that, so it's going to take us a little while. Okay? So if we're going to use that, we have to go from miles ultimately to inches and then centimeters back out to kilometers. It's kind of like, really? 5,280? Very good. Exact relationship. So we don't have to count 3 sig figs there. Okay, how about feet and inches? 12, right? 1 foot is exactly equal to 12 inches. Okay, and then what about, oh, here's one thing. So instead of going, a lot of times students will go directly from centimeters to kilometers thinking, well, you got the centi, it's a -2, or the factor of 10 to the -2nd. And kilometers, you add another 3 zeros, so that's to the negative, or to the 5th. But what I would do is go through the base unit. The base unit here between centimeters and kilometers is meters. So one of the things you need to memorize is the relationship between centimeters and meters. And you can say it one of 2 ways. You can say that you can say, yeah, I guess this is the best way to say it. There are 100 centimeters in 1 meter. And then to go to kilometers, okay, 1 kilometer is equal to 1,000 meters. Then we're done. Phew. All right, so let's knock this one out. I won't belabor it too much. First term is going to be the same term as before. The thing we want to convert, 120 with 3 sig figs, 120 miles. So in this case, we're going to go to feet next. So we're going to use this relationship between miles and feet. So we're going to put 1 mile on the bottom, 5,280 feet on top. Then we're going to go from feet to inches. And so we're going to put 1 foot down there and 12 inches up there. And then we're going to cross the Imperial Bridge. And so we're going to put 1 inch down here and 2.54 centimeters up there. And then we're not going to go straight to kilometers from centimeters. We're going to go through the base unit meters. So I'm going to put 100 centimeters down here and 1 meter right there. Or over here. 100 centimeters down here, 1 meter there. And then finally we're going to go to kilometers. So we'll put 1 meter down there, or we'll put 1,000 meters down there and 1 kilometer there. So, phew. Rounding wise, does it look like we need to round the same way? 3 sig figs? So 3 sig figs there. No uncertainty there, so I don't care about the rounding. This is exact, so I don't have to round. This is exact, so I don't have to round, or I don't have to count sig figs, excuse me. Exact, exact. Okay, 3 sig figs. Not so surprising. Got the same answer. Yeah, I know. So sometimes students will ask, well, which way do you want me to do it? And it's like, whatever works for you. Okay, switching gears a little bit. We are going to take speed and we are going to use it as a tool or conversion factor to go back and forth between distance and time and distance. Because speed is like a physical property of this bird. Okay, this bird is flying 14 meters in 1 second. So how far will it fly in 2 seconds? 28 meters, exactly. How long will it take to get 7 meters? Half a second, exactly. So, I mean, those are the things that you've done in your mind. I'm going to show you how you can write them down, factor label way. So in this case, we want to know the time. How long will it take the loon, if the loon flies 5.00 kilometers? How long will it take him to go 5.00 kilometers? Now, when we worked at other problems before, I said always start with the term that you want to convert. And when we work this problem, I'm going to start with this term that we want. This is what we want to convert. Basically, we want to convert distance to time. Just kind of like we did a minute ago with the 7 meters to a half a second. By the way, that thing with the 7 meters to a half a second, here's how that looks. I want to go 7 meters, and I'm going to use this physical property. And we've learned factor label-wise that if I want meters to cancel, do you buy this? That's it. That's what you did. Okay. If you divide this out, 7 divided by 14 is 0.5. The inverse of 2. And what would the units be? Seconds. Yeah. Actually, the units, yep, are just seconds. So this physical property, this distance of interest, and this is the time of interest. Okay, so let's knock this out. Okay. So that physical property of that loon that's flying 14 meters in 1 second, you know, it could change that. You know, it could slow down, it could speed up, but that's what it is right now. And we're going to use it, like I said, we can use it, you did use it to go back and forth between distance and time. So physical properties like that we can kind of think of as a ratio, 14 meters per 1 second. And that physical property is the same if we're saying it in 1 second it flies 14 meters, or it flies 14 meters in 1 second, same depth. Okay, or we can even make it into a quality, you know. So that's why we kind of have it at our command. So I guess the one other thing we need to do on the front end of this is your distance was given in kilometers, instead of meters. And your speed is in meters per second. So you're going to have to link that 5.00 kilometers to meters first, and then you can plug in. Okay, so we get kilometers to meters. We get meters then to seconds using that speed of the flying loon. And we're done. So the first term over 1 is going to be that 5.00 kilometers. Oh, thank you. So we want a time in minutes? Takey. Okay, now we're ready to knock it out. 5.00 kilometers. Convert it to meters by putting, what's going to go down here? Kilometers, very good. 1 kilometer, 1,000 meters. Yep, 1 kilometer, 1,000 meters. Then we're ready to use the loon speed. So what goes down here? 14 meters, perfect. And 1 second in the top. Very good. Then we don't want to leave it as seconds. We want to go all the way to minutes. So what goes down here? 60 seconds. Up there. 1 minute. You got it. And that's it. So let's put check marks over things that we need to count sig figs for. All right. So do we need to count sig figs here? Yes. 3 sig figs. Do we need to count sig figs here? No. Nope. How about 14? Yes. How many sig figs? 2. Very good. Now, the 1 we don't need to, because it was divided out that way. So, okay, how about the 1 or the 60 here? No. Cool. So how do we need to round it? Here. You got it. 6.0 minutes. I was trying to think if that's very fast. I don't know. What? Kind of fast?
5 kilometers in 6 minutes.
Okay. Yeah. Okay. So, yeah, I know, but you guys turned these in today. So it'd be the rest, 33, 34, 35, and 36. Are due Wednesday, yeah. And I do check my email. And for this class, just because of, I'll give you my phone number. So you can text me or call me. And if 319-750-5991. So that's my cell phone. Use it wisely throughout the semester. Because sometimes you've worked on it a while and you're like, oh, whatever. So just call me and we'll see what we can do. Okay? This reminds you to show all your work. And so, any questions? All right. So let's take it up a notch. We did, take it up a notch, still using the factor label method. So, there's a yardstick up here. So this is about 3 feet. Okay. So if this is 3 feet, and I lay this down here, so I have 3 feet by 3 feet. So the question would be, how many? By the way, if this is 1 yard by 1 yard, that's 1 square yard. Okay. And the question would be, how many square feet are there? 9. There are 9. Oh, spoiler alert. So we're going to kind of do this the factor label way. Okay, so that's the 9 square feet in 1 square yard. Okay. So clearly, each yard was 3 feet. So 3 feet times 3 feet gave you an area of 9 square feet. Okay, that all works. Well, let's go ahead and set it up using the factor label method, where the goal of this is to basically, we've been kind of mapping out what we're trying to do. I think I'll do it this way. We want to take 1 yard squared, and we want to get to question mark. You told me this question mark's 9, which I agree, feet squared. Okay. So the relationship is, or what we're going to do, is we may not know directly, well, feet, blank feet is equal to 1 yard. What goes in that blank?
3.
3, yes, exactly. So if we use this equality twice, we can do a factor label problem. Going from square yards to square feet. If we use the 1 yard over 3 feet twice, or sorry, 3 feet over 1 yard twice, it works. Does that make sense? Okay. Good. Cool. Just to kind of reiterate what we got going. That's over 1. So yard squared is 2 yard terms. So this cancels both of those. Units we're left with are 2 feet units, which is the same thing as feet squared. Numbers we have are 3 times 3 are 9. Very good. We could have right here for this equality, we had to use this twice. Alternatively, we could say 3 feet squared is equal to 1 yard squared. The deal here is I put the quantity, I put the 3 feet in parentheses and the square outside. Okay? And when you do that, you have to make sure that, like all good parentheses, that square outside the parentheses is brought in to everything, the number and the units. Okay? You'll see what I mean. Okay. So that was 2 dimensions, but more than likely in chemistry we don't care about area as much as we honestly care about volume. All right. So if we were looking at, again, sticking with the English yards and feet and looking at, instead of square, cubed, we could come up with this relationship between cubic yards and cubic feet. The catch is that, as I said before, if you want to come up with a nice equality between yards cubed and feet cubed, that's cool. But remember that that 3 comes in and applies to that 3, or the cubed needs to come in and apply to the 3. So what's 3 cubed?
27.
It is. Thank you very much. So you're going to see, I think I rewrite this. You could also, this could be expanded out as 1 yard cubed is equal to 27 feet cubed. Okay? Little pitfall there. All right, so let's do a problem. And it does cross the imperial bridge, because we're going to go from inches cubed. No, it doesn't. It stays in the English system. We're going to go from inches cubed to feet cubed. Shouldn't be too bad, because we know the relationship, the exact relationship. 1 foot is exactly equal to 12 inches. We're good with that. So in 1 step, we should be able to do that. 22.0 inches is equal to how many, inches cubed is equal to how many feet cubed? So the first term is going to be that inches cubed we want to convert over 1. We have some options here. One of my favorite options is to simply put 1 foot over 12 inches, 1 foot over 12 inches, 1 foot over 12 inches. In doing that, I see those 3 inches terms cancel, and I know I'm left with 3 feet units, which is feet cubed. Alternatively, we could go right for the juggler and put 1 foot over 12 inches quantity cubed. And in doing so, then with regard to units, we have inches cubed cancel, and we're left with units of feet cubed. The catch here is, just like we had to cube the 3 to get it 27, we have to make sure when we multiply it out that that is 12 raised to the 3rd power. So in our calculator, we're going to have to put, 22.0 in the top divided by 12 cubed. Okay. All right. Now I went ahead and showed you the answer. How many sig figs are the answer? See fingers? Don't need any toes? Yes, 3. 3. This 0 is not significant. And you see that 3 sig figs came from these 3 sig figs. All right. So just to kind of reinforce what this quantity means, I prefer this right here, writing the single, the non-squared or cubed term 3 times. Okay. All right. Now let's go from English to metric with regard to volume. Alrighty. So this is a classic where what we're going to make use of is this fact. And you'll see it on the next slide. How would you fill this in? Blank centimeters cubed is equal to blank milliliters. What numbers go in there?
1 and 1.
1 and 1, yep. Very good. So we're going to make use of that fact. You'd be like, well, why are we going to do that? And basically, you're going to see on the next slide that we're going to go from inches cubed to centimeters cubed. You think we can do that? That's that one relationship you're going to have to memorize. And then we can go from centimeters cubed to milliliters, because it's a 1-to-1, but you have to show your work. And then we go from milliliters to liters. Okay, so I'll go ahead and formally show you that. Okay. So inches cubed to liters, we're going to go through centimeters cubed. And then we're going to go to milliliters. That's a 1-to-1 relationship. 1 centimeter cubed is exactly equal to 1 milliliter. Then we can go to liters. 1 liter is equal to 1,000 milliliters. So let's knock this one out. We'll start with the thing we want to convert over 1, 25.0 centimeters, 25.0 inches cubed over 1. Okay, next term. What goes in the bottom here? Inches cubed, very good. What goes in the top?
Centimeters.
Yep, centimeters cubed. And however we do it, we need to make sure that we're going to cube that 2.54. Does that make sense? Okay. It applies to the units, centimeters, and the number, 2.54, because it's quantity. Very good. So now we're at centimeters cubed, and we're going to go to milliliters. So what goes in the bottom here? Yep, centimeters cubed. What goes in the top? Very good. Okay, oops, sorry. Then we're going to go to liters. So what goes down here at the bottom? 1,000 milliliters. Perfect. What goes in the top? liters, 1 liter. You got it. That's it. There's only one number that has uncertainty in this series, this little calculation here. What number is it?
25.
Yep, 2.50. How many sig figs? 3. Very good. So, do it in your mind. Okay. So this is a case where we had to show a trailing 0 after the decimal, 0.410, to give us 3 sig figs. Good? You look good with it. Here are some problems that will be due. Let's take a look right quick, just because we can. Okay. So, there was one problem, and I kind of brought in, this is from yesterday. It's problem 4B. It's not a problem, but it's one of your calculations. So one of your calculations, you guys had that plastic vial, and you got the mass of the water in that plastic vial. And you're supposed to take that mass, use the density of water at that temperature, which we got from a table, and you're supposed to use that mass and density and knock out volume. Okay, so actually, finally, this is where we're going to talk about it. But it kind of reminds me of the speed of the loon. You know, we said that loon was flying, 14 meters per 1 second. That's like a physical property of the loon. Okay, when they give a density of whether it's water, in this case methanol, they give a density, that's like a physical property of that solution. We can use that to get back and forth however we need to. So you're going to see me unpack this density of methanol here in a minute, but our 2 problems we're going to do is we are going to go from volume to mass, specifically 242 milliliters to mass of methanol using that density. And then the other type of problem, we're going to go from mass, specifically 50.0 grams of methanol, to see what volume that would be. Okay, it's similar. I could ask you similar questions about the, let's see. 2 milliliters of methanol would weigh about 1.6 grams. Does that sound right? Okay. I mean, you can just eyeball it, and we're going to do the same thing. That is a ratio. So what I encourage people to do is if you're given that number, like density number flat, 0.792 grams per mil, flat, okay, I would fluff it out like this. So we can get ready to plug it in and make units cancel that need to cancel and be left with units that we need to be left with. Okay, so here we go. Let's knock out A and B. Okay, the first one. The first one we were trying to find the mass given this volume. So we start with the volume over 1. Okay, and do you see where we're going to use we're going to use what I say is the non-flipped version of density, the 0.792 grams per 1 mil. So mils cancel. That makes sense? That's it. So what units are we left with?
Grams.
Grams. Perfect. Is there uncertainty in the 242 mils? Yep. Is there uncertainty in the 0.792 grams per mil? Yeah. So 3, right? So the mass, is 192 grams. Cool. That's it. Let's do the second one. In this case, we're going from mass to volume. So I would put that over 1. Now we want grams to cancel. So do you see we're going to use the flipped version of density? 1 milliliter per that 0.792 grams. Then grams will cancel. And we're left with units of milliliters. And that's it. Is there uncertainty in 50.0? Mm-hmm. And so there is uncertainty here. How many significant figures? 3. There are 3. Yep. 63.1 mils. It's a very practical little problem to be able to do. And this is very similar to your 4B. Okay. Let's use weight percent as a conversion factor. And you're going to see me fluff that 7.2% by weight out. Basically, they said somebody made a sugar solution, and it's 7.2% sugar, okay, by mass. So we can use a weight percent like that and as a conversion factor to go back and forth between grams of the component, in this case sucrose, and grams of the mixture. Let's see. And this will help. So let me show you how I fluff out that weight percent. That's how it was given. Anytime parts per 100, 7.2%. It means in 100 grams of the solution, the sugar water, you have 7.2 grams of sucrose or sugar. So that's a physical property of that particular solution. The cool thing about mixtures like that is, you could make it more sugary, less sugary, but that's this one's weight percent. So I'll tell you right off the bat, doing problems, weight percent problems, students, we all struggle. We need to recognize that you have grams of two different things. Grams of the component, by definition, per 100 grams of the mixture. In this case, sugar solution. So you're going to have to keep grams of what? Grams of sucrose per 100 grams of solution. So we could flip it if we need to. The inverse is awesome. Okay, in 100 grams of solution, there are 7.2 grams of sucrose. We could flatten it out. Okay, those are all different ways of thinking of that physical property we can use as a conversion factor. So we use weight percent to go back and forth between grams or mass of component and grams of the mixture. All right. So in the first case, we wanted to know how many grams of sucrose there are in 65 grams of solution. So this is where we need to kind of focus on, we want grams of solution to cancel, so that's going to go down here. So we're going to use the non-flipped version of the weight percent. Okay, so 7.2 grams of sucrose per 100 grams of solution. Grams of solution cancel, we're left with grams of sucrose. That's what we're done. Is there uncertainty in 65? Yep, there's uncertainty in 65 grams. There's uncertainty in almost everything, except the metric system and the whole 1 inch is exactly 2.54 centimeters. There's uncertainty in everything. How about is there uncertainty in the 7.2? Yeah, there is uncertainty in 7.2. There is no uncertainty in the 100 because that's by definition. We unpacked that. 7.2% means that there are approximately 7.2 grams of sucrose in exactly 100 grams of solution. Okay, so 2 sig figs. So 4.7 grams of sucrose. So mixtures like this can be separated back out into their components, sugar and water, by the physical means. We could just evaporate it, right? Looking at the second one, we were given grams of sucrose and wondered how many grams of solution we'd need to set aside to get that mass of sucrose. So in this case, we're going to use the inverse of that weight percent. We're going to put the 7.2 grams of sucrose, 100 grams of solution up there. Grams of sucrose cancel, we're left with grams of solution. And that's what we're trying to get to. So 2 sig figs. So 46 grams of solution is what you'd need to set aside if your goal was that much mixture, set aside that much mixture if you wanted to get 3.3 grams of the component. The thing with all problems, physical problems, chemistry problems, is it doesn't hurt to take one step back and look at it and say, does that make sense? Like, okay, I could buy that. And if it doesn't make sense, you have a couple of options. One is just to turn it in anyway, and the other is to kind of go back and look at it again and look at it again. As I was looking at my solutions, you know, that I post and you guys have access to, I remember years ago taking a course similar to this, and I mean, I spent hours poring over, trying to make it mine, you know. So if you spend hours poring over stuff to make it yours, you're in good company. Right. All right. Very good. Oh, yes. I forgot this problem. Okay, this is another good one. This uses both density and weight percent. So one of the first things I'm going to do is unpack density, 1.13 grams of nitric acid per 1 milliliter of solution, and weight percent. Let me see. I might want to, I'm leaning towards leaving this so we have a little more time. Let me see what those problems are. So these are the ones you need to do also. Oops. 52.
Are you right?
I am, I think. 52? Maybe not. You're right, I'm not. $53, $55, and $56. Any questions? Okay. Good. Have a good weekend.
This is nice. I know you were talking about this in class earlier. I don't understand this problem. Like, I have my math and my water.
I see it right here.
Okay. So I know that, I know it's 18.3 grams over 1, but then I don't understand what to do from there.
Okay, and then this is what we talked about in class, so the density of water is at that temperature, what is 90,
Yeah, okay.
2-3 grams.
So I just times them together?
And so,
Okay.
yeah, and so if you put 1 mil over that grams,
Mhm.
units of grams can't.
Oh, okay, I was making it way more complicated. Okay, thank you.
So, did you get it figured out then?
Yeah,
Okay.
thanks.
Well, for our last calculations we did the other day, I already got like the regular stuff photocopied off, but did you want the calculations photocopied off as well?
No, because you're gonna need your original, we're on the same track.
Yeah, I've got the original still.
Yeah, the
in my-
original,
It's somewhere in here.
but it's on a separate piece of paper, you didn't fly it. Yeah, yep.
Okay.
So, so if we didn't write our pre-lab in our book, we're okay, but just next time write it in our
Right.
book?
Yeah.
Okay. I didn't know if you like looked at it at the end of the semester
No.
or, okay,
And just each, at the beginning of each
class.
lab, yeah.
That's due
Okay.
Thursday, right?
The pre-labs are always due before lab starts.
No, the write-up on
Yes,
our lab.
they're
Okay.
right. And I'll tell the whole class, but like if you're running late, you can have the whole day Thursday, like as until midnight Thursday. And then you just need to beat me to my office over there.
Mine will be done by then, so don't worry about it.
Yeah, hopefully I can bug you Wednesday and have you look at it.
That'll be good.
Have fun.
Have a good weekend.
You too. Are you feeling any better, David?
I'm feeling like worse.
Dang, maybe you need to go back.
Last night I felt like crap, and then I went to Walmart a little bit ago and grabbed some like cold and allergy medicine, because